Okay. So, sorry. To my knowledge, it hasn't happened that I've gotten through a lecture, but not so far yet. Trust that you guys will let me know. All right, so last time we talked a little bit about idempotents and about how their existence can give us a sense of what ring we're dealing with. And so the main kind of idea there was if E1 and E2 are complete orthogonal idempotents, and the commutative ring R then E1R and E2R are both rings, not subrings per se, but they're rings, commutative rings, and R is isomorphic to the sum of these two, or the product. So in some sense, you're decomposing your ring into two more elementary rings. It's something mathematicians love to do. Take something complicated and simplify it. So the example I gave last time was Z6, but I want to kind of give a general picture here, general example, which is, let's say we just have R equaling Z mod and M, and M are just say positive integers. And we'll assume that they're relatively prime. Their greatest common divisor is 1. Well, one thing we know in this case is we know that we can have this theorem that allows us to find integers, say A and B. There exists A and B, which are just integers, such that A times N plus B times M equals 1. That's the greatest common divisor. Now, what you'll notice, so this finding these A and B's is basically the Euclidean algorithm. There's this algorithm that is essentially the algorithm that'll return these coefficients, which I'm not going to go over. It's just element. You can crack open any number theory book, or I don't know when you learn this. I think you learned it in elementary school at some point and you forget it. But it's a basic algorithm. It's not. So, well, what you can see in here, but my point is these are computable numbers. A and B is things you can get pretty easily, like successive divisions and binary numbers. So, what you see in this equation, though, is the following, which is you can note that AN, I take their classes, are complete orthogonal. Well, they sum to 1. So, but if I take this equation and I multiply the whole thing by, say, AN, and here I get AN squared, here I get AN, and here I get something divisible by N and M, so it's 0 in R. Make sense? So that's just saying that it's an idempotent. Same thing applies with BM. So you get these two idempotents. Okay, so what's the big deal? Well, the big deal is you can then solve some equations once you know this. So, well, one thing it tells you is then what we did last time. R is isomorphic to, well, AN times Z mod NM and BM times, okay, I'll write it out. NM plus BM. However, these are easy, you can easily show that these are isomorphic to Z mod M and Z mod N, respectively. Strings. In fact, the map, which is the projection to one of these, is just multiply by AN. Like, let's say we wanted to know what this isomorphism was as a map. So I take something here, and I want to get what the first factor is in its isomorphism. Well, just multiply it by AN and take it mod M. That will be the same. That's not like completely obvious, but it's that will work. Let's see this illustration of this and how this is. This goes under the name of the Chinese remainder theorem. Which you can express with several different. So I'll just give a big example. I'm doing 2 idempotents, but you can do like a whole system. You can like as many as you want. There's no ortho. So, but I'll just do 2. So suppose N and M GCD as above. Then there's a solution, more or less unique. A solution to equations. X. It's a pair of system equations. You can see mod M X D mod N. You can write down, and again, you can write down a list of these. If you have pairwise relative prime, you can write down a list. I tried to think of, I mean, there's some silly, I hate giving like math problems where it's like, you have so many cookies you're making or something like that. But you want to divide them equally and eat 2 or something, whatever. I don't want to do something like that. So but I had trouble. I think I'm sure there's a lot of applications of this. In fact, there's like a sort of sorting problem that I was tasked with. We have like, 2,000 students or something, and we have all these rooms. So the problems like this, where you have to like divide people up evenly, and I was writing a program and I came across needing something like this, but it's not quite this. Anyway, there's real life problems where this will come into play, I want to say, but I didn't. So how do you prove the Chinese remainder theorem from this observation here? Well, if I pick my C and my D, I can make a single element in here. What the theorem is saying is that there's actually an integer, which actually is unique mod N times M, that will be sent to precisely this pair when you reduce mod N. That's the proof. All right, so let's do it in practice and see what I'm talking about. Let's say I set up so I'm not going to prove this independent of what I just said, because it's just, I don't think it's necessary. You want, thank you. Let's say we have these 2 equations. I wrote these sort of randomly, but then the answer is kind of simple. So I have these two equations. And I want to solve them both simultaneously. I want a single X that will solve both of these. And of course, you can solve them individually, but you want to double point in solving them at the same time. So what you do is you look at 7 and 15, and you look at that equation, and it looks like 15 plus negative 2 times 7. This is equal to 1. In this case, it's not. I'm trying to make it hard, but there's like a threshold where that's a harder problem. I think you need them to, you need sort of their difference to be kind of awkward, like not big and not too small or something like that. So now you've got two, but the point is you've got two item codes here. Two item codes. And so all you have to do is multiply, right? I mean, so this map to Z mod 7 across Z mod 15. This is going to be multiplying here by 15, which is the A times M or something. A times N. So map, this is going to be multiplying by 15. So this is going to go to 1. And this is going to be multiplying by negative 2 times 7, which is negative 14. So if I want something, I want it to go to 2 here and 3 here. Well, just multiply by 2 and 3. So I want 15 times 2 here, negative 14 times 3 here. A pair of elements. Pair of numbers. So what's going to get sent to that? Well, what's going to get sent to that is the element 15 times 2 plus negative 14 times 3, which is 30 minus something. Yeah, guys, 42. All right, so 30 minus 42 is negative 12. For some reason, so this is, I think this will be okay. Maybe you don't like negative numbers. And that's where the uniqueness part is. We know that this is unique mod their product, which is 105. And so you can add a multiple of 105, and you'd add 105 to this. So if you added 105 to this, you'll get what? 93 or something. So you can check 93. Yeah, 91 is divisible by 7. So 93 is congruent to 2 mod 7. And mod 15 is congruent to 3. So this is like, it's kind of a magical thing. I mean, it's not that. So if you wrote down harder numbers here than 7 and 15, I mean, maybe you could do this by hand, like you could just kind of play with it. But if you give these types of problems to people, the uninitiated, it's like they'll bang their head against the wall for a day or two. Like it's not very fun. so it's kind of a nice application of what we're doing, is that you can get these types of solution equations. Okay, I won't. Questions? Okay. So the next section in this chapter has to do with fractions. We all love. My kids love fractions. Yeah, they do like fractions for like years with children. I don't know. I mean, I I mean, I've like blanked out on my entire youth, but like, yeah, they do like fractions forever. Like my son's been doing fractions. Like, how do they spend that much time on fractions? I'm very curious. I think it's because people never learn them and then they want to, well, or maybe it's the thing that they're most comfortable with. Okay, so fractions are quite complicated though, but not okay. There's two things that are there's two different things. One is fractions in the context of commutative rings. That's not hard. I'll just mention this. Everything is commutative here for us. I'm going to make another constraint too. But and let's make it okay. So this I want to say commutative R, not hard. Integral domain R, which I'll define in a second. Really not hard. Non-commutative R. That's harder. That's hard. That's hard. You do things in the non-commutative world, you do localization, depending on the context. Some contexts are not as hard. It can bring you right up to the current level, current research type mathematics, like localizing categories. It can be hard, or at least interesting and subtle. However, commutative integral domains really not hard. Let's talk about those. What is an integral domain? I think I might have said something about this. Remember? This is a commutative ring, no zero divisors. Now, some people will call that a domain, and then some people, when they say domain, will mean a non-commutative or not necessarily commutative ring with those. So there's some language there, but integral domain, I think everyone accepts means this. So why is that helpful? Well, that's helpful because you have a cancellation in integral domains that you don't necessarily have in general. So if R is so in such a ring, this is an equivalent way of defining these rings. If AB equals, well, let's say A, sorry, let me call it C here. AC is equal to BC, with C not equal to 0, then A equals B. And cancel C. That does not mean you can divide. Okay, that's not what you get. You cannot divide in rings. Divide in rings, you're in fields, and that's just a much different and easier subject. That means you can cancel. Why is this true, by the way? You guys can tell me that. Why, if I have a ring with no zero divisors, why is this hold? I'll give you the hint, and I'll be like, okay. Thank you. Hint. Hint. Subtract. AC minus BC equals 0. Am I doing the left? A ring, all these properties, might as well use them. Yeah. It's A minus B times C. Now, zero divisor is something that you can write as a product with some other thing. It's not 0, you get 0. We said C is not 0. Since there are no zero divisors, A minus B must be 0. All right. But sometimes it's tricky. It's like, these are things that, because I'm old and been doing this forever, it's like, just glare at you. But when you're first starting out, I do remember, just looking at an equation, subtracting, moving everything to one side, it's not necessarily instinctual, right? You're used to dividing, you're used to doing other things. Okay. When we have this, you do want to be able to divide. You do want to be able to multiply by C inverse. It'd be nice to be able to have such elements at hand. And that's the fact that you have this property that, A equals B in these cases, allows you to easily sort of define fractions, define a ring of fractions. But let me just mention, there are certainly plenty of domains, or plenty of commutative rings that are not domains, not integral domains. So example of non-domain, well, you guys can tell me, are not domain. What do you think? What are your rings? What do you go to? I always try to have my students, as we go along through these kinds of topics, to sort of build up a toolbox of, which you can think of as sort of like examples that you can grab out and play with and just get a sense as to what's right and what's wrong. So for groups, you should have some basic groups. You should have integers, have the dihedral group, symmetric group, right? You should have some things that you could grab onto and say, okay, does this work in this case? Just so you get a sense of it. Rings should be the same way. You should have the integers, polynomial rings. What other ones? What about a finite ring? Finite rings? Talking about those a second ago. Z mod n. So what about Z mod n? Are there zero divisors in Z mod n? Take two elements that are non-zero in Z mod n, multiply them together and get 0. Wow. Always? N is not prime. If n has two factors that are smaller, I can take those two factors as non-zero congruence multiply them together, and I'll get n, which is 0. Something like Z mod 6. This would be a good ring, sort of. Well, I mean, Z mod 4 would work too. 2 times 3 is. So there are a lot of these. And in fact, that whole class of examples, product rings, if I have two non-trivial rings and take their product, that's always going to have zero divisors. Like take one factor comma 0, 0 comma that other factor, some take a product with 0, component wise. There are a lot of things like this. But they're not, in some sense, they're not nearly as interesting. Well, I don't want to say that, but they're actually, oftentimes you want to distance yourself from them. Anyway, there are plenty of integral domains out there to play with. So let's play with one. Let's play with it. What can we do with an integral domain? So assume R is an integral domain. Well, we want fractions. So we do what we learned in elementary school. We just make them. We're going to define another ring, define a field. Well, it'll be a field, but first we'll define a set. It'll look like A over B. A and B are in our ring. And you learned in elementary school that B should not be 0. So we'll assume B is non-zero. This is a big set. Now here's the problem with this set. This set, well, is not a very good set. If I'm doing fractions, I don't want this set actually. I want this set to be something else. Because first of all, it doesn't make any sense. Because what is this? That was supposed to be narrow. What is the arrow? What is that? I mean, I just put a bunch of symbols together. So maybe this should really be, I should have written it this way. This was sensible, right? That's in the, I know how to create tuples. Let me do that. This is actually a subset of a standard thing of R across R. As a set. That's something reasonable. Now I'll think of it as A over B, but I don't want to do that. Because is this a good set for fractions? So if I think of it this way, I write that element that way. Is that how I really should think of fractions? What's the subtlety of fractions? There is subtlety. If you're doing this construction. So I go to my son. Well, my son now won't talk to me about fractions, which is fine. Talked enough about it. But my daughter, she'll still do it. She's just starting her very long fraction journey. So I'll go talk to her and say, hey, have you ever heard of 6/3? And she'll say, Dad, stop talking to me about math. That's 2 over 1, right? And I'll say, no, it's not. It's 8 over 4. And she'll say, these are all the same fractions, but they're not the same here. Not the same. They're different elements. I don't want that. I want them to all be the same. So what do? Well, we have this thing called an equivalence relation, right? Might as well use it. Let's call them all equal via an equivalence relation. So we need to define a partition of this set, and the elements of that partition are going to be our fractions. So we'll say AB is related to CD if, well, if you have an equation, this is just our thought bubble here. We want to say A over B equals C over D. Well, that's going to be true if I can like cross multiply, right? A times D equals B times C. So there's my relation. If A, D equals B, C. Now you can prove that this is symmetric, transitive, or flexible. Therefore gives you an equivalent for any integral domain. If you're not in an integral domain, but are in a commutative ring, there you have to modify the set. There's a modification. If you're in a non-commutative ring, you're in trouble. There's a set of conditions called Orr's conditions that you have to check, and all this kind of nice test. This now I'll write A over B for the equivalence class. Now it's sensible. I remember what notation we use, brackets or something, bars. Okay. And when I choose these different ways of writing my fractions, I'm actually choosing different representatives of that equivalence class. Pairs of integers that represent the same equivalence class. Okay. But yeah.
What does the bar mean there?
So it's the equivalent. So this is equal to the set of all. It's whenever you define an equivalence relation, you partition your set. So if I take an element of that set and I want to understand and I want to write notation for that subset for which that element is a member of in the partition, I'm going to put a bar over it. I don't remember what I used before. It's been too long. I don't know. I may have used this. May have used like AB with the tilde. I really don't remember. Look back in the notes. I'm sorry. But it's defined to equal all CD so that AB is equivalent to CD. There are different notations in different books, and that's why I don't remember. Some people use all sorts of different notations. But we'll write it as A over B, a new notation, or an old. Now we do everything that we would expect. So now define arithmetic as in elementary school. How do you multiply fractions? Numerator times numerator, denominator times denominator. A over B, C over D. How do I add fractions? That's always a little bit, more of a reason that 2/3 of the population hates math. AD plus BC. But, what can you do? These you can check, and I'm not going to, but you can check that they satisfy all the ring axioms, associativity, so on. Distributive property, everything works as expected. And you can check the unit 1 will be equal to A over A for any A not equal to 0. Of course, it wouldn't be defined to have A over 0. 0 an element of our separate partitioning. And 0 is equal to 0 over any. There's ambiguity in the notation, but that's okay. We'll learn to deal with it with the equivalence. But this first one tells us if A over B is not equal to 0, which means A is not 0, B is not 0. Then, it's not going to be a shocker to any of you, but okay. A over B times B over A. Again, using commutativity, gives us AB over AB, which is our unit. Which means all of the elements in this ring, all the non-zero elements in this ring have inverses. We made a field. Yay. Started with a ring, an integral domain. So we had some conditions on it. Built a field. Also, we can take our ring and we can actually injectively map it to this new thing. I'm going to call this new thing something now. The right. There are a lot of different I'm going to write I like this notation best, I think, right now. Fractions, field of fractions of R. Let's just write this for the set fraction. So really it is the set of equivalence classes, but okay. There is a homomorphism, which is injective, 1-to-1, sends an element, A, which is the fraction A over 1. And so you can include your ring into your big field. And it is bigger. You should be thinking of it that way. The way you should think of this field, it is huge, actually. So that's actually kind of its drawback, is that when you start with a ring, if you're studying rings, sometimes it's very discrete. You have like some finite generators, you can work with them. You go to the field of fractions, it's enormous. All of a sudden it's not even finitely generated over the ring. It's not something like the rational, going from the integers to the rational numbers is taking, this discrete spacing and filling it in with this massive, dense set. It's not super complicated, but it's a lot more complicated than the integers in some sense. Yeah.
Are there finite integral domains that we can do this in?
Finite integral domain. I want to say a finite integral domain is going to be a field. So you can do it, but you're going to end up, if you start with a field and you do this, this will be an isomorphism. The reason that I want to say that, let's prove it. Good question. Very good. However, there are rings that that are like characteristic P, which are infinite, where you can do this and get something. So if you start with a finite R integral domain, you take an element A in R, say it's not 0. Well, then you can you can consider A squared on. And at some point, you're going to get a repetition, right? Finite. So you'll get that A, some integer, is equal to A to some other integer, say M is less than N. And then you can subtract as to do the same trick, or you can cancel. Let's do cancellations in integral domains. So I can see 1 is equal to A to the N minus N. Equals A times something, A to the N minus. So there's an inverse. Your finite, your integral domain, your field. So this is primarily applied to, this is applied to more infinite settings. And the two main examples that we have, of course, already learned about are integers to rationals. And we have, if you think about calculus, you have talked about and certainly studied rational functions, which are just, these are just fractions of polynomials. In fact, if you look at the language that's used there, it's the same language as is used for integers. And that's because this is really a formal thing you're doing. Okay. So, but the point is you can do this with all kinds of things. You can do this with all kinds of things. And it's a fun thing to do, and you learn a lot about your rings, and there's a lot of applications of this. I want to say you can study a lot. Of course, you can also do things like take, well, okay, so other examples, I'm getting a little sloppy here. Other examples. Would be something like take the integers, square root of 2, get join the square root of 2 into the integers, and if we take their field, we'll still just get the rationals with the joining square root of 2. That's because you know, again, from elementary school, well, I don't know about elementary, maybe middle or something. 2 is equal to square root of 2 over 2. So you can kind of invert the square root of 2 and actually look at it as a multiple rational. So there are things like that. Now there's a theorem that this inclusion is universal in a sense. In fact, there's a whole notion in mathematics, which is an undergrad class, so maybe it's not as typical to emphasize it, which is the notion of universal properties. And so you can characterize this field as the unique field satisfying the unique up isomorphism, satisfying a universal property. And here's the property. So I won't say much about this, but read it in the book. These are very important for abstract mathematics, for higher mathematics. I don't know how much. So another way of explaining what field of fractions of a ring is, this is the unique field. And when I say unique, it's unique up to isomorphism. In other words, you could maybe get 2 of them and label things differently, but there's an isomorphism. Satisfying the following. But one, R includes into this field that we construct. And then 2, if F is any other field, if F is any field, and we have an inclusion, to F, then we'll try doing it this way. Then there exists. So then what you can do is you can take, this is sort of like a timeline thing. Take your first inclusion and realize, okay, you have 2 inclusions into 2 fields. And once you see this, there exists some new homomorphism. Making a diagram from you. That means that the compositions are the same. That means that if I start here, I go this way, and then here, it's the same as going this way. Function. Composing these 2 functions gives you this function. What is it saying? It's saying if I have some big field and I can put my ring in it, then I can certainly put all the fractions from that ring into that field because everything's invertible in that field. So while the integers may go to some huge field, if it's in a field, the inverse of all of those integers in that field, I can write as fractions, and I can send fractions to those inverse. That would be this map. So it's some object that satisfies this property, and this is actually very kind of important in mathematics. Everything's important. Okay, so that's about all I want to say about fractions. There's all kinds of variants of this, by the way. Like maybe you don't want to invert everything. You just want to invert some things. There's whole techniques called localization for that. And these are the big thing people do in algebraic geometry over and over and over again to make things well more amenable. Okay. So the last section for this week, which I don't have a huge amount of time for, but I've already covered a little bit of it, talks about maximal ideals. So I'll just recall a couple of things about these. So I think Artin defines them the usual way, which is fine. And which is just a maximal ideal is a maximal ideal. So the biggest ideal you can get in a ring without it being all of the ring. So there's no proper ideal containing it properly. It's sort of as big as you can get. But he has the proposition that maximal ideals are precisely those ideals for which if I quotient by them, I get a field. The same that we did, same result we did. He also has a proposition, which is kind of a nice, interesting proposition, which is that maximal ideals of the integers are principal, well, all the ideals of the integers are principal ideals, but they're principal ideals where he is prime. You know that, right? I mean, because what happens when we quotient by this ideal? We get Z, if we quotient by the ideal generated by A, we get Z mod A. And as we just talked about a moment ago, if A is a composite, then there's zero divisors. So that's not a field. There are no zero divisors in a field. You can't have divide zero and be invertible at the same time. Unless you're like the zero ring. So, and I'm just not taking any words with that one. So there's an analog to this proposition. So analog for polynomials with coefficients in the field. And for that, we need to have the notion of irreducible polynomial. So let me just write that here. F of x in polynomial algebra is irreducible if f of x when I write it as a product. If when I write f of x as a product, either g or h is constant. The proposition says that maximal ideals of f of x are the principal. I mean, again, this is also a principal ideal domain. So all of the ideals are principal ideals. But now the maximal ones are ones where f is reducible. And in the final minute, I just want to draw your attention to something, which is behind what I think we're going to talk a little more about. If you look at this definition of irreducibility, you could replace constant with a unit. Constants are units, I mean, as long as they're on zero. If you do that, this is very much like the definition for prime integer. An integer is prime if when I write it as a product of two other integers, one of them is 1. So it's not divisible by two non, it's only divisible by itself and 1. Why do we call it irreducible then? Why do we call this prime? And the reason is that there is, I don't know if it's a historical accident, probably. There is a notion of prime, called a prime ideal. So A and R is prime. I won't prove this. This is also not hard. If A is prime, a prime ideal, which means that's the same thing as saying R over this ideal is an integral domain. That's a definition. One way of defining it. Turns out that primes are not the same as zeros. They are for integers. They are for polynomials. But there are a lot of rings where they're not. And this discrepancy is behind a lot of interesting mathematics. And actually in geometry, it's behind a lot of interesting mathematics. So, and kind of is a fusion between geometry and number theory and algebra, all kinds of analysis. But I don't know how much we'll talk about it. We'll talk a little bit about it, but I think I'm at time. So have a good weekend. I'll be here for problem session at 3:30.